last rank drop.
All right, so let's chit chat about that assignment from yesterday, okay, in terms of like a bigger idea. So if you look on number 1, you got 100 milliliters of 0.2 benzoic acid, it's called HA, and you have a Ka value, right? The 6.4 times 10 to the negative fifth. So right away, you have a Ka value. And you'll see this later on. The value, numeric value of K will tell you which direction the reaction is going to go. When you have small K values, which are less than 1, if you look at all the K values, okay, they're all less than 1. All the Kb values are less than 1. So what that indicates is when you look at the forward reaction of hydroniums plus anions, and this thing ionizing, when you have a K value that is less than 1, that indicates that the forward direction of that reaction is not favored, okay? The reverse reaction is favored, okay? And that's true whether it's Ka, whether it's Kb, or eventually we're going to get into something called KSP, which deals with solubility. So the smaller the K value is, the less likely it is to go in the forward direction. And again, look at how you calculate K. Ka is that hydronium ion concentration times the anion concentration divided by HA. So the only way, mathematically, that you can get a Ka value less than 1, and it's always products over reactants. And that's the other thing that you'll see. When we write expressions, it's always products over reactants. Always, no exceptions whatsoever. So the only way I can get a Ka value less than 1 is if I have very small concentrations on top and very big concentrations on the bottom. That's the only way that can happen. And the smaller that Ka value is, that means the smaller these numbers are up on top. Okay, so that's one big idea. So here's what I want you to look at. When you look at number 1, and you're trying to calculate that initial pH, I want to point out something that's important. That initial pH on 1A should be like 2.45. Okay? So that should be your first answer on 1A, 2.45. Because what's happening is that, first off, you have that Ka value. Mother Nature is a lazy prima donna. Mother Nature is going to adjust those hydroniums and that anion concentration, and when you divide by HA, that's the number Mother Nature wants, because that's when Mother Nature is in equilibrium. Okay? So, when you get on, and this is going to be important, when you get that X value, which is your hydronium ion concentration on 1A, you should get 3.6 times 10 to the minus third as your molarity. Now, just bank that number for now. So weak acid, when it reaches that equilibrium point, that's the concentration of your hydronium ions. Okay? Take the negative log of that, boom, you get your pH. Now, when you look on number 2, if you look at number 2, notice that when I wrote this up, you got a 0.2 molar solution of benzoic acid. And what's going to happen on number 2, I also gave you a 0.2 molar solution, but this is a strong acid. Okay, so here's what I want you to see is the difference. So when you have this hypochlorous acid, HClO4, which is a strong acid, that, by definition, completely ionizes. Okay? What this means is that if you set up this rice chart, and here's the difference. If it's a strong acid, you start off here at 0.20000. All of that ionizes, plus 0.2, plus 0.2, and you get 0.200. So here's what I want you to see is a huge difference. When you did 1A, which was a weak acid, when it reached equilibrium, the concentration of the hydronium ions was 3.6 times 10 to the negative third. when you have a strong acid, because that's why I typed this up. That's why I gave you the same molarity as the weak acid and the same molarity as the strong acid. The start off is 0.2. But if it's a strong acid, the hydronium ion concentration becomes 0.2. So out of curiosity, somebody have a calculator handy? Okay, Evan, take 0.2 and divide that by 3.6 times 10 to the negative third.
55.5 repeating.
So about 56?
Yeah.
So what that means is that the ionization on that strong acid is about 56 times greater than the ionization is on the weak acid. Okay? That's what makes the difference. Okay? So this is why your pH on 2A should be 0.70, because you're taking the negative log of 0.2. Your pH on 1A should be 2.45. Now, if you look on number 3, you've added no potassium hydroxide. That pH on that one is 2.72. Okay, so those should be your first answers. 2.45, 0.7, 2.72. Those are the first answers on the first 3 problems. Now, let's say on the quiz, I said I'm going to give you 2 Ka values. One is 6.4 times 10 to the negative fifth, which is up like there on number 1. And then on number 3, I'm going to give you a second Ka value of 1.8 times 10 to the negative fifth. So you have 6.4 times 10 to the negative fifth, and then you have 1.8 times 10 to the negative fifth. Okay? All right? It's cool. Which one is the stronger acid? The 6.4 times 10 to the negative fifth or the 1.8 times 10 to the negative? Which one is the stronger acid? Evan?
The 6.4 times 10 to the negative fifth.
Why? You're right.
A higher Ka value means that you need to have more on your numerator for the hydronium concentration times the anion concentration.
Fantastic.
That needs to be bigger.
It's a wonderful answer. So if you look at how you calculate Ka, it's a simple idea, but that's how you really understand these problems. The only way you can have a bigger Ka value is if you have bigger numbers up on top. Okay? And the more it ionizes, the stronger that acid is. The less it ionizes, the weaker the acid is. But here's your dichotomy. Remember, the weaker the acid it is, the stronger the conjugate base is. Okay? Because that's that dichotomy. So when you look at, this is a tug of war. And fundamentally, this is what happens on an atomic level. You take a strong acid and you put that in with a water molecule. The water molecule is going to have a stronger attraction for that proton and that anion than the molecular form for itself is. That's what allows it to ionize. Okay, so water is like a break point. It's a tug of war. If it's a weak acid, okay, if it's a weak acid, you put that in water. Water doesn't have as strong as an attraction as the anion does. The anion is more likely to pull that back together. That's why it exists as the molecular form. So it's a tug of war. If it's a weak acid, the conjugate base has a stronger pull than the water molecule does. If it's a strong acid, the water molecule has a stronger pull, and that's why it ionizes. Okay? Now, the kickers on these are the ones where you get to like on 1E when it's completely ionized. No, you're not going to have a question like that on the quiz today. You are on the next quiz, but not on this one. Okay? So your answer to 1E, so you have an idea if you got that right, should be around 8.5. Okay? Because what's going to happen, and this is the most important step. So what's happening like on 1E, here's your reaction, plus hydroxides, yielding water and the anion. Okay? So here is what's important. This is the conjugate base off of a weak acid. So what's going to happen is that when this is all gets neutralized, that anion reacts back with the water. This acts as a base, and here's that reaction, yielding the acid and hydroxides. Okay? So this is where you have to go through, take the millimoles, divide it by the total volume, so there are some things that you need to do. First off, when you set up that rice chart, when you do that secondary reaction, this, listen to me, has to be in molarity. It is not moles, it is not millimoles. When you set up this secondary rice chart for that secondary reaction, it has to be anions as a molarity. This is going to be 0, 0. Minus X, plus X, plus X. Now, on the quiz today, I'm going to tell you straight up, I'm going to give you a weak base, okay? Not sure what the weak bases are, you can look at the back of the book. Oh, here's some list of some of the weak bases. So your weak bases can exist in one of two forms. Like we're going to go over next door, and I'm going to show you like one, the classic one is ammonia, and I'll show you a reaction that's going to happen with that. So you can have actual weak bases, which is, there's a list of that either on your equation sheet, or you could just go to the back of the book and find the Kb values. The other way that you can get a weak base is that you pull the anion off of a weak acid, okay? And that's what's happening here. So your weak base can either be an anion, or it can be a molecular form like ammonia, okay? Hydroxides, very, very strong base. Hydroxide is the ultimate, give me the proton kind of thing, okay? This one will too, but not nearly like the hydroxide will. So, this has to be molarity. Take the millimoles divided by the total volume. So here's what's important. When you find X, you're finding your hydroxide ion concentration. So when you take the negative log of that, you're finding your POH, subtract that from 14. So your answer to 1E should be around 8.5. And then you're going to do that same type of complex calculation when you get to number 3E. So that answer to 3E should be around 8.8. Okay? It's an ish, but it's be something around 8.8. Okay? Your answer to 2D should be 7.00. And here's what I want you to see is the difference. On number 2, you have a strong acid. On 2D, you've completely neutralized the acids and bases. You have the anion in the solution, but it's not going to create a secondary reaction. They're there, but they don't alter the pH of the solution. So that's why your answer to 2D, because you've completely neutralized it, is just 7.00. But your answers on the other ones where you have a weak acid, that pH is higher because that creates a secondary reaction that generates hydroxides, which makes the pH go up. Okay, that's what I want you to see is the main difference. All right, any questions on that assignment? Hopefully this is becoming like, oh, I got this. It just kind of becomes repetitive. You just kind of have to do this again and again and again. Okay, we're good going. Let's go try something. Okay, stop that camera. Let's go. So what I just gave you is kind of more of a Chem 1 thing more than about anything. So I always get the scores from last year's AP tests, and it kind of breaks it down into category. And the kids do really, really well on the complex stuff, but they seem to be not doing as well on like the basic stuff. So this is why I have this. So it talks about like isotopes. Remember, isotopes have the same number of protons, different numbers of neutrons. So it's going to ask about Ernest Rutherford's. Okay, so when you get into like question number 2, so let me give you a quick refresher on Ernest Rutherford's experiment. He was the one that shot. He had a radioactive source that would randomly decay and it would shoot out, he called them alpha particles because he didn't know what they were. Turns out they were a helium nucleus, 4, 2, 2 plus. It was just a helium nucleus. Now, everybody has this perception that you could actually see these particles being shot out. You couldn't, okay? The only way that they detected that these particles were even there is that when they was hit like a phosphorescent screen, they would emit a small flash of light. So, the short version of this is a much longer discussion. Rutherford knew they were positively charged because he put a positively and negatively charged plate in the path, and these particles would be deflected away from the positive and towards the negative plate. That's how he knew they were positively charged. So he put this sheet of gold foil. Gold foil is unique because you can make it basically one atom layer thick. And to our eyes, it appears solid. So he shot these particles through there, and surprisingly, almost every one of those particles went straight through. Okay, so it would be like me throwing a tennis ball at that wall. To us, it appears solid. In reality, most of the tennis balls would go straight through. And every once in a very, 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 very great while, like literally 1 in a million, what would happen, that particle would hit, it would turn around, and it would bounce back. So because those are positively charged, what Rutherford concluded was that the nucleus is extremely small, extremely dense, and positively charged, because that's the only way two positively charged particles could bounce back. So here's the analogy in terms of like scale. So imagine I'm standing on one end of the football field, and on the other end of the football field there is a volleyball, and a single volleyball. And I'm going to shoot marbles at that volleyball that's on the other end of the football field. And most of the time, those marbles are going to go straight through. Every once in a while, I would hit that volleyball just right, where it would bounce back. Okay, so keep that in mind. You're answering the questions about Rutherford. So I'm planning on spending some time on Monday discussing this. But a lot of this, hopefully, is old school Chem 1 stuff. Evan.
So, did he expect them to bounce back? Because did he have like phosphorescent screens behind them?
Oh yeah, we'll talk about that. Because they were at that point all about the plum pudding model. So they didn't have a mechanism to explain how a positively charged nucleus could exist, because they hadn't found the strong nuclear force yet. Okay, so you have time for I know you May South people need to go, so are you going to dance your way out?
I mean, I can.
Yeah, it's up to you.